So it almost goes without saying that the quality of food that we consume every day is a fundamental determinant of our health and well-being. In fact, if we take a look at the list of chronic illnesses or even global epidemics, including diabetes, cardiovascular disease, etc., you can quite easily see quite a few of them are essentially nutrition-related diseases and can be largely caused by long-term consumption of low-quality food. As a result, it's easy to conclude that food quality measurement and characterization is very important. I'd like to actually elaborate this point a little bit more with two examples. Imagine on the left side you can see that a mother went to the grocery store to pick up milk. She may want to ensure that there is no adulterants or antibiotics in the milk. On the other hand, you may have just served yourself a freshly squeezed apple juice and want to make sure that there is no trace amount of pesticides inside that homemade juice. In both of these scenarios, a liquid food characterization unit could be really useful. And the democratization of food quality measurements by a low-cost, mobile, ubiquitous computing system could first of all enable consumers to track food quality before purchase, and more importantly, it can put an indirect pressure on the food industry or government regulators to ensure quality. And this has been basically the basic inspiration behind the paper that I'll be presenting today. I'll be presenting Nutrilyzer, a mobile system for characterizing liquid food with photoacoustic effect. My name is Tawhid Rahman. I'll be presenting the paper today, as you can see. I'm a fifth-year PhD student in the Department of Computing and Information Science, currently working with Dr. Tanzim Chaudhary in the Piezoelectric Computing Lab. And thanks for attending my talk. Okay, so I wanted to start off my presentation with a quiz, and I want participation from you guys. So in the next slide, I will basically play back a video of an experiment that I ran a couple of weeks earlier. And you have to tell me where the humming noise in the video coming from and what would be the fundamental frequency of that hum. I'll actually disclose another piece of information with you. That is, in that experiment, I used a halogen bulb, a pickle jar, a microphone, and a tea light candle. Okay, here you go. Volume. Yeah, we checked it. How about that? Yeah. So any guess? I guess you already have seen the answer. We actually just listened to the sound of the bulb, right? And it is due to the photoacoustic effect. So before I present a formal definition of photoacoustic effect, let me actually walk you through the setup of the listening to the sound of a bulb experiment that I have run a few minutes. So I essentially started off with a glass jar, pickle jar that I bought from Walmart. I deposited soot in one side of the jar. Soot is basically carbon black, a very pure absorber of light. Then I placed a microphone, doesn't have to be main microphone, in the jar. And then lastly, I placed a halogen bulb in front of the jar. And as you can already imagine from the name photoacoustic, photoacoustic effect is nothing but the generation of sound from an intensity modulated light. Essentially, in this particular example, everything started with the halogen bulb, right? As the halogen bulb is essentially powered by alternating current, and here in the US, the frequency is 60 hertz, right? Essentially, the brightness of the halogen bulb is getting modulated at twice the frequency of the alternating current, which is 120 hertz. So we get intensity modulated light that falls on the surface of the soot, or carbon black, and getting absorbed due to optical absorption. So what's happening is the soot is getting heated and cooled iteratively, right? And this heat and cooling process is getting transmitted to the adjacent air inside the jar, which in turn is giving rise to a generation of a pressure wave, which we can hear with the microphone. So this is kind of the full story. And now if we take a look at the spectrogram of the signal that I've recorded, here you can see a presence of 120 hertz photoacoustic signal almost throughout the entire session, except when I block the light and by placing a piece of paper, essentially. And obviously, we're not the first person to work on this kind of concept, right? In fact, the discovery of photoacoustic effect dates back to the year 1880, when Alexander Graham Bell was experimenting with long-distance sound transfer with sunlight, voice-activated mirror, and a selenium cell in a project called Photophone. And a very fun fact about this project is, actually during his lifetime, he considered Photophone to be his greatest invention, even greater than telephone, which is very interesting. Anyways, while tinkering in this project, accidentally he discovered that sound was getting produced directly from the solid sample when he was exposing it to the beam of a rapidly interrupted sunlight. And the resulting sound wave is dependent on the type of material, essentially due to optical absorption. And the same phenomenon can be observed with invisible part of the electromagnetic spectrum, essentially NIR, for instance, right? And the most fascinating thing to me, at least, was he observed everything correctly just by relying on his manual audition or ear. At that time, there was no sensor. So pretty much the same reason the whole thing was pretty much confined within applied physics books, right? And it's until 1940s when we started to get good sensor, good quality microphone sensors, and also good sources of electromagnetic wave, researchers and scientists started to build photoacoustic systems. So a traditional photoacoustic setup would look something like that. It's kind of the modern version of the traditional setup, right? No wonder it's bulky, expensive, power hungry, has almost no portability, and definitely not for mobile usage, right? Mobile sensing. I would like to remind ourselves the goal that we have in this paper. We want to design and implement a low-cost, portable, mobile photoacoustic liquid food sensing system. And the gap, essentially, that we want to bridge is the gap between a traditional photoacoustic system, the bulky one, to a low-cost, portable, mobile photoacoustic system, right? Let me quickly walk you through a traditional photoacoustic system and tell you how we are planning to actually design our system. So a traditional photoacoustic system starts with a broadband light source and a monochromator so that we can select particular wavelength, right? We have actually achieved pretty much the same thing with an array of LEDs with varying wavelength. We have, as you can see, we have used 16 LEDs, surface-mounted LEDs, and could implement it in a very small place. Then the next part that the traditional photoacoustic setup would use is the mechanical chopper to intensity modulate light. Essentially, it's like a fan. It will slice off the continuous light wave, right? And create an illusion of kind of intensity modulated light. We have achieved the same thing with digital switching, right? We don't have to bother with all this mechanical stuff. Lastly, the bottleneck part of a traditional photoacoustic setup is a hermetically isolated photoacoustic cell. It's essentially isolates the target analyte material in every sense, and it contains a microphone so that the photoacoustic cell can act as an acoustic resonator and help the microphone to capture the sound, because the photoacoustic sound in and of itself is very weak. And we kind of don't need the hermetically isolated photoacoustic cell because we have used a piezoelectric sensor, and there's no need for sophisticated material transportation mechanism that traditional setup used. Essentially, with a light emitting diode and piezoelectric sensor duo was kind of at the core of our design. And in the next couple of slides, I'll try to kind of illustrate how with these two components, we can actually generate photoacoustic effect and listen to it. So the setup is very simple. Take an LED. I used a lens to collimate the light and focus on the surface of a piezoelectric sensor, and I modulated the LED, right, with 4 hertz. This is what we get. The top sub figure, the dotted line represents the LED status. As you can see, as soon as the LED is on, the raw photoacoustic signal is trending up, right? And during the absence of light, it's going low. We can easily filter it out with median digital filtering, quite easy, and get the filtered photoacoustic signal. Now the question is, what do we do with it, right? The most important parameter that we can extract from the filtered photoacoustic signal is the peak-to-peak distance. In other words, the photoacoustic signal strength, right? We can also call it photoacoustic amplitude. The reason why this is so important is essentially now just by analyzing the sound, we can tell how much optical absorption that happened with that material. So now you can just analyze the sound, but you can talk about how the light interacted with the target material. There was a bunch of set of parameters. I don't have time to go over a series of experiments that we have conducted. You can find the detailed experimental result of the paper. Essentially, we ran a series of experiments to select the set of parameters in order to maximize the photoacoustic amplitude. And this is the basic takeaway. I won't go over into it in detail, but we incorporated all these takeaways in our consecutive experiment that we have run. But things are not too interesting with just one LED and one piezoelectric sensor. Things get a little bit more interesting when you start to use an array of LEDs. Here you can see we have used an array of LEDs with varying center wavelengths. And now, if we actually extract the corresponding photoacoustic amplitude for each of those LEDs separately, it will form a photoacoustic spectra, which actually captures the absorption spectra of the target material. Let me show you how. So each LED is blinked for 15 times before it moves to the next one, right? And in the bottom sub-figure, we can see the running peak-to-peak distance, right? And if you look closely, you can see there's a bit of transient response before it kind of saturates or reaches its steady state. And we can quite easily avoid that, get rid of the transient response by capturing the median value and assigning that as the photoacoustic amplitude of the target LED. Now, we have actually run the same experiment for a bunch of solid material. As you can see, for aluminum, brass, and copper. And the corresponding photoacoustic spectra for each material is uniquely different and are essentially capturing the optical absorption spectra. So now this is useful for perhaps classifying solids, right? You can tell now whether it's brass or aluminum or copper. But again, this is not too useful for liquid classification, the chemical composition of a liquid. Now let's do one thing. Let's place the analyte liquid solution in the middle of the light and piezoelectric sensor. So now, if we extract the photoacoustic spectra with the analyte solution, it not only now depends on the absorption spectra of the piezoelectrode, but also depends on the transmission spectra of the liquid. We can quite easily extract the transmission spectra, which is by normalizing the photoacoustic spectra with the analyte solution by dividing the photoacoustic spectra without the analyte solution. Essentially, now if we take the normalized spectra, our hope is that it will contain enough information that will indicate so that we can map it to the target chemical composition. So this has been the basic kind of physics behind the talk, the paper that I'll be presenting today. Now let's talk about system implementation, right? So here, you can see a cross-sectional diagram of the system that we have implemented. On the left side, we have a PCB board that's kind of holding the microcontroller, a bunch of LED control circuit, and an array of LEDs. So this is how it looks like. Web development, everything in the lab, in-house. So at the heart of the implementation, we have a ARM microcontroller unit, right? And then the ARM microcontroller unit essentially has two responsibilities. First responsibility is to intensity modulate each of these LEDs sequentially. And here we have used a LED driver, right, that converts the constant voltage source to constant current source so that every time you modulate the LEDs, it will give you constant intensity. The other responsibility of the ARM microcontroller is essentially to listen to the generated photoacoustic signal in the two piezoelectric sensor that we have used. And obviously, the signal conditioning circuit is amplifying the weak signal. So now let's go back to the design. So right in front of that PCB, we have placed a light tunnel so that it can steer all the light to the direction, so that to the direction of the cuvette, which contains the target analyte liquid sample. And if you notice closely, we have used two piezoelectric sensors, and the reason essentially one is essentially placed facing the beam, light beam, and other is perpendicular to it. Essentially, the reason is with two piezoelectric sensors, we're not only capturing the transmission spectra, but also capturing the scattering properties, right? And our hope is the normalized photoacoustic spectra at piezo 1 and piezo 2 will help us to paint a better picture of the target chemical composition that we want to actually map it to. This is what the final product looked like. Now it's time to evaluate our system, right? So we actually designed a series of experiments here as well. So at first we didn't put our system to the most toughest challenge possible, right? We wanted to see if we can actually essentially characterize colored dye water solution in terms of color type and concentration of color prediction. Once we have more kind of confidence on our system that it can do that, we went ahead and put it to test in terms of characterizing liquid food, specifically looked at milk protein concentration prediction, adulterated milk classification, and alcohol concentration prediction. So now let's talk about the color characterization in dye water solution. So here you can see the normalized photoacoustic spectra of piezo1, which is capturing the transmission spectra, right? And for 4 different colors. And these are the 4 different solutions that we have used in this experiment. As you can already visually differentiate between them with our bare naked eye, what we expect? We expect that we will be able to do that, the same thing, just by looking at the visible part of the spectra, right? We don't really need to bother about the near-infrared part of the spectra. So let's shade it out, and if we look closely, we can easily see that for red dye water solution, the photoacoustic amplitude corresponding to the red or reddish color LEDs are much higher, right? And it is essentially because a red solution is producing a higher forward scattering for red or reddish wavelengths. In fact, the same thing you can see for other colors like green and blue, and for black, as we expect, black is good absorber, or it won't let any light through it, so it actually yields a very low photoacoustic signal. In fact, we can expect the same thing the same effect of forward scattering if we see through a colored glass or a beaker filled with colored solution, right? So now if we look at the normalized photoacoustic spectra at piezo1, capturing transmission, and at piezo2, capturing scattering, we can see that photoacoustic spectra is essentially uniquely different across different color, and what we expect, we can easily map it to classify different colors, right? So this is good. So now it's time to see if we can actually predict concentration. So we went ahead and created 4 different concentrations of a particular color, that is blue, with blue dye. And here's the result. So here we can see the scatter plot between the photoacoustic amplitude produced by blue and another bluish color LED, right? Because we expect that the photoacoustic amplitude for in the blue region will be the maximum, right? Now if we look closely for water, right? And it is at piezo1, so it's capturing transmission, remember. So now what you can see essentially is for water, it yields a very high photoacoustic amplitude, as it's letting all the light through it, and all the light is essentially hitting the surface of the piezo1, right? And as we increase the concentration of the color dye solution, what happens, a lot of scattering happens. So not all the light, all the photon can actually reach the surface of the piezoelectric sensor. As a result, it yields a very low kind of photoacoustic signal. And essentially, we can use these 2 features to predict the concentration. A little bit more interesting thing happens for piezo2, which is capturing the scattering. So now the water is at the bottom right corner, right? Now what we expect? We expect that as we add more and more dye to it, there'll be a lot of more molecules that will actually scatter the light and steer it toward the side piezo2, right? Which is positioned at the side, actually. So a higher concentration essentially gives rise to a higher scattering and a higher photoacoustic amplitude at piezo2. But if the concentration is too much, then actually it kind of cuts off the light altogether, so which yields even lower. So there is a time when it actually comes back as we increase the concentration. Anyway, so we can see there is some non-linearity in the system. So we used a linear network to train the system. We have achieved very good result, that is about 0.98 correlation coefficient with 14% root relative squared error. So we're satisfied with our experiments. So now it's time to see if our system can actually characterize liquid food. So the first experiment that we designed is in the context of milk protein characterization. We have run 3 independent trials for each of the 4 milk solution. And we ran a leave-on trial out cross-validation with neural network. And the correlation coefficient that we got is pretty impressive, I would say, 0.90 with a root relative squared error of 16%. And here you can see kind of the error bar for predicted milk protein in terms of concentration with respect to the actual milk protein, right? And you can see all the levels are quite well separated. The next step, we actually tried out if our system can characterize meat adulterants. So we produced a bunch of adulterated milk in the lab. So we started off with 100% whole milk. We added detergent, salt, starch, and water, which are actually very common milk adulterants. Surprisingly, I was pretty surprised when I learned about that. And on the right side, you can see the recipe. And when we go ahead and run our 3 independent trials and put it to machine learning algorithm, after selecting the best feature, what you see is we can easily achieve about 80% of recall. Here is the scatter plot between the 2 most dominant feature selection algorithm. Feature selected by this feature selection algorithm. You can see it's kind of well separated. Another very interesting thing was that if you look closely, you can see both of the 2 most important features are actually coming from piezo 2, not piezo 1. And we can expect that because adulterated milk is colloidal in nature, which gives rise to colloidal particle scattering, which is also called Tyndall scattering, right? So piezo 2 is actually if anything that has high concentration, we expect that piezo 2 will play a much dominant role if you want to classify it or somehow characterize it. Lastly, we went ahead and tried to predict the alcohol concentration. We actually tested it with 2 different alcohols. One was a colored alcohol, 85% rum. It has a brownish tint to it. We collected 3 independent trials from 6 different alcoholic drink solutions. And we get about 99% correlation coefficient. Actually, it's not as good as you think because we are kind of getting help from the fact that it has a color. So some of the visible spectra photoacoustic amplitude is actually helping us to predict it more accurately than it probably should have. So we went ahead and actually tried it also with clear alcohol that doesn't have any color whatsoever. It's 95% clear alcohol, and we see a decrease in performance, a significant decrease actually. Although correlation coefficient is not bad, but the root relative squared error is pretty bad. It's essentially happening because we don't have a lot of IR LEDs in the beyond 1,000 hertz, nanometer. So if we could have some more interesting LEDs at those wavelengths, we could potentially improve the result. So in summary, we have explored the fundamental concept of photoacoustic effect with step-by-step experimentation. We designed and implemented a low-cost mobile photoacoustic sensing system, Nutrilyzer. We validated the Nutrilyzer in the context of liquid colored dye constant characterization and a bunch of milk protein, milk adulterants, and alcohol concentration. Now, the question is what's next? Obviously, our immediate goal, as long as this project is concerned, is to perhaps run a few more iterations and evaluate the liquid food characterization unit that we have in the wild and see if it can actually make a difference to real people. There are actually a lot more interesting future opportunities that I am particularly, being a mobile health researcher, really excited about. A mobile photoacoustic system can actually image deeper into the tissue, human tissue. And so if we can build it with the lower cost, it could potentially tell us a lot of interesting parameters that is related to human tissue, including glucose, hydration, and stuff like that. Another very fascinating thing is actually another very positive side of photoacoustic system is it can predict you materials that is inside in another kind of medium, but present in trace amounts. So things like this is very fascinating to me. So there are some initial laboratory experiments that shows that transdermal diagnosis of malaria is possible with this technique, right? Which is actually lives in the nucleoli of RBC, which is very, very trace amount. Lastly, something that I'm currently doing, I am trying to make light bulb great again by making it keep an eye on the indoor quality. I did some initial experimentation, but in coming days, perhaps I'll share some more results in another conference that we'll meet. Thank you, thanks a lot for paying attention to my presentation, and I'd love to take some of your questions.
Thank the speaker. So we have time for some questions.
Did I make it in time?
Yeah.
Okay.
I'm just wondering why did you use the photoacoustic effect rather than
Right.
diode or something
Right,
like that.
right. So there are a few, I didn't really I didn't run any experiment and compare my setup with a photodiode-based setup. But if you look at the literature, I can talk about it from the literature's point of view. So essentially, if you look at the, can I go back to? Here. Essentially, if you look at the whole kind of path of photoacoustic signal generation, you'll see it's not only actually dependent on absorption of light, but all the other kind of thermoelastic processes are actually impacting the system. So first of all, people has already demonstrated that photoacoustic system will be really useful if you want to detect any trace amount of, existence of trace amount of liquid in another medium. So that is one reason. In fact, you don't need a lot of preparation. So in diffuse reflectance-based approach, if you have a material that scatters a lot, right? So then you actually need to at first prepare it and condition it before you can test it. For a photoacoustic-based approach, you don't need it, and there are existing literatures that talk about it. So there are a lot of reasons why you'd actually prefer a photoacoustic-based approach, which means converting the light to a sound wave and then analyze the sound wave rather than directly using a photoelectric effect, essentially. Right. So yeah, essentially that is the basic reasons. But in coming days, I guess I don't have a complete answer to that because I didn't run A/B testing between those
yeah, I think that'd be really cool to see if there's like a large difference between those two things. The other thing I was wondering is like when you put the adulterant in the milk or in the alcohol or whatever, was the difference in the measured absorption related to like the way that the adulterant modified the chemical properties of the milk? So like when you put like say like salt or detergent in there, was it because it congealed the proteins in there and it was actually the congealed proteins that were changing the absorption spectrum, or was it the salt itself that was, you know what I'm saying?
Yeah, I think both will impact. So salt, it depends on how that target material is chemically reacting to the milk, for instance, right? So if I don't know much about like the chemistry of mixing salt with milk, but if it reacts, it's probably changing its molecule in some way or changing its chemical properties. So what we essentially are looking at is how the light is reacting while it's passing through the system, right? Before we analyze the photoacoustic signal.
Okay. Yeah. Cool. Thanks. Great work.
Thanks.
So unlike a tunable laser, which is what is generally used in these systems, you had to select some 16 specific wavelengths. Was there a motivation for selecting the 16 ones you had?
Initially, we wanted to, because we didn't know what we can really do with it, we used a few UV. I have a list with it somewhere, but anyways, we have a few, 2 UV, a few visible spectra, and few NIR. Pretty much at the very beginning, honestly speaking, my choice of LEDs was pretty much confined within what's available in the market, because I didn't know what's going to happen. But if I'm asked to select a set of LEDs right now, what I'll do is I'll look at the absorption spectra. So let's say I want to classify caffeine in coffee, right? I'll go ahead and do my research and look at the absorption spectra or transmittance and scattering spectra of caffeine inside coffee, and look at interesting curves that is making it, like what's actually changing, which part of the spectra is changing if I systematically add coffee to it, right? So ideally, we should select a set of LEDs that capture that interesting part of that particular spectra, which is actually changing due to the target chemical, addition of the target chemical. So now, if you ask me to do, caffeine characterization, I'll go ahead at first do some research on the transmission spectra and then select accordingly. But anyway, another point is a tunable laser was very expensive. So I wanted to get a tunable laser, but it's a cost in the range of $2,000 to $5,000, especially if you go and want to select something in the range of NIR. So I kind of avoid that route altogether.
Okay, so you envision
maybe we can take this question offline.
Oh, yeah.
Yeah, okay.